food.
Okay, here we go. Final presentation of the semester.
Hi everyone. So this is our last team for this project for this course. So this is called the distributed ETL with Scalable Web Deployment, and this is the content of the presentation. So starting first, here's the context of our project. So let's say if the client provided us with some European soccer database from Kaggle, and we are trying to build a machine learning model to predict the winner of the next match. We can win, and so work on this machine learning project. What we are going to do is starting with the data processing step, where we will do some data cleaning and feature engineering stuff. Next, when the data is ready, we will try to develop the model and maybe do some improvement. The lastly is to visualize the data with some dashboard web application. And to make it more clear, see, here is a machine learning workflow, but we will focusing on the data processing and the development of visualization tool. So here's the focus and our tech stack. For the data processing, the task we are going to do is exactly extract general rating for a team based on a team's previous match records. So the data will be thousands, millions of records of previous team match. And I will use AWS S3 RDS for data storage, AWS EMR, ElasticMapReduce under the Hadoop framework to do the distributed data processing. For the visualization tool, we will use the Autoscaling tool from the AWS, and we will visualize with Plotly Dash web app. And the AWS, the Amazon EKS will be used to make it scalable. The test will be conducted with Apache JMeter. So starting with the design. I was in charge of the ETL step, or data processing step. So basically, you will start from gathering the data from the S3 buckets to using the user-defined scripts, either Java or Python scripts. And the MapReduce task will transfer the data into the format we want. Lastly, the data will save to RDS databases. And initially, I was trying to explain what MapReduce was like, but Mitchell explained in the start, so I'll skip this part. So my MapReduce pipeline will be like the input data will be as introduced before, match records, including ratings for all players from both home and away team. The map task will try to calculate mean ratings. So for each record, each row of data, it will calculate the mean ratings for all players in one team. So there will be two teams. So you will write 2 times for 2 teams. The shuffling task will just group the mapping output with the same keys together. Reduce task will calculate also for all data ratings for the same team, you will calculate the mean rating. And output data will be saved into the data set. Initially, we plan to implement the whole workflow, including the model development and deployment. However, we don't have time to do that. So here comes with data design of assistant design of the dashboard.
Yeah. For our structure part, actually, we are using Amazon EKS to make the life easier instead of going through implementation and configuration or implementation of the Kubernetes by ourselves, step by step. So EKS is going to make the life way much easier. And we are going to use a horizontal pod auto-scaling service. And after that, we are using Helm, which is a package manager, which you can, for example, simply can install whatever package you need on your Kubernetes cluster. And after that, we are using metric server, which is responsible for sending the metrics, for example. But when I'm saying metrics, for example, CPU utilization, memory utilization, all the metrics that is available on the worker nodes that you can see here. So we have an Amazon Elastic Kubernetes service and 3 nodes. And an auto-scaling group consists of 3 nodes, which on each node we can run, using HPA or horizontal pod autoscaling, we can run multiple pods, as you can see here. And also, I do like to mention that Kubernetes operation view, which is, I find it that it's a very interesting service, which it's kind of monitoring service that you can see, what's going on your Kubernetes cluster in just one dashboard. How many nodes do you have? How many pods are running on your nodes? And what's CPU utilization, or for example, memory utilization, or all this kind of information. You can find it on Kubernetes operation view. And after that, we make a microservice using, we make Docker image of Flatly service and run it on our node. And I'm going to pass it back to Forrest again.
Yes, so here's the season testing and analysis for ETL section. So I have set 5 scenarios for my ETL test. They vary. The global configurations will set up the controlled variables, and to ensure that each of the tests will be conducted under the same environment, if not the same, as similar as possible. So the scenarios vary in number of instances, languages to use, and the number of master nodes and core nodes, also known as workers. So the input data, as explained before, it is a bunch of boring data like this. So for one record, there will be the previous, all these numbers are the ratings for the players in the team. And the last 2 numbers are the home team ID and the away team ID, which will be the key for the map task. And there will be we have 3 files to test. So there will be 3 data points. Each of them vary in number of rows. And the output data will be in the key value pairs of team ID and the ratings for each team. As you can expect, there are more boring data from the output data here. So this will be one record of the data. However, the interesting part is coming. So here are 2 questions we are going to investigate. Do we use Python or Java to do the MapReduce task? The more instances, will that performance be better? So the first question is, if we use Python or Java. So it's easy to understand that Python is easier to code, but we need some third-party APIs to achieve the MapReduce under the Hadoop framework. The one I chose was the MRJob package, and I heard from the suggestion of Daniel later after I done the implementations. PySpark may be a good choice too. And for the Java, it's known as unfriendly for data processing tasks. Nobody uses Java to do this, and it's such difficult to write code. So, but when implementing in Python using the MRJob, I encountered the limitations of our AWS Academy. We are not going to, we cannot create AMI roles or users. So initially, I was trying to implement everything in Python, but later on, I just transferred to Java. And also, Java has the advantage of using the native MapReduce implementations. So here are some controlled variables I tested under this question. The result will be from the scenario of 4 and 5, and they are under 1 instances. So the wall time for Python and Java with different number of records are here. So it's obvious that Python is faster when processing a smaller number of records, but the Java is good at the time will be so much faster when the amount of number of data is in huge number. And also something more interesting is when we look at the throughput, Python's throughput so there are 2 throughput. One is the records per second, number of records per second. And another one is megabytes per second. So they are basically the same diagrams. And the interesting is Python is consistent in performance for different number of records. But Java there is a huge performance increase in Java when processing the large number of records. So here comes the answers. We can use Python when the batch size of data is small. In my case, it's 5 gigabytes for each file. And Python has the advantage of fast development. But we need to be aware using Java will increase the speed a lot. So it is super good for efficiency purpose. And other thoughts I saw from Hugo's Piazza test that he mentions JSON. And later on, I think maybe that is a way to maybe implement it faster in the data processing tasks. And PySpark, as I mentioned, may be a good is because it's popular in doing such tasks. And the question too is maybe does the more instances means the better performance? Look at these two graphs. The answer could be maybe, because the number of the processing time and CPU usage are much more faster when we have more number of instances. So from instances number of 2 to 4, the performance is increasing. However, when we look at the throughput, we might see that the throughput of records per second are megabytes per second. So when we are processing smaller number of data, the throughput is almost the same, only like 500 megabytes difference for smaller number of records. So the answers could be maybe consider your budgets first, because the more instances you have, the more expensive you face, and the size of matters. Same as question 1 answers. Maybe no more when data is smaller than 5 gigabytes. Consider use smaller number of instances. Another thing is to consider is maybe we can consider maximize EC2's resources usage before increasing the sizes. I'll explain more in the next slide. Next one is maybe consider using EMR task nodes. I realized that after all the implementations that the task nodes is more efficient because it's specifically used to power the performing parallel computation tasks. But I was using the other type of nodes, which is not a smart choice. And also another thing to consider could be maybe balance the number of internal map tasks and reduce tasks. So for the EC2 usage, resource usage, we can see an interesting curve here. So this is graph of P99 CPU usage versus the gigabytes per instance. So we can sort of predict how much CPU power usage will be when we increase the number of the size of files to process per instance to estimate if we should have more instances or fewer. And another one is to consider maybe here to balance the number of internal mass tasks and reduce tasks. During my implementations, I can see a huge number of the huge increase of map wall time per mass tag. Wall time per mass tag. It can even come to like 8,000 milliseconds, but the wall time per reduced task is relatively small. Maybe something like, and the real line is the why it's the expected situations where the wall time between the reduced task and mass task are the same. So here comes the implementations of the Dash app, the testing.
So here's a test scenario for the infrastructure, for the auto-scaling infrastructure, which you can put whatever application or the front, the application that the Forest was working on it. But right now we are using just a simple instance of the Plateau Dash, and we are using Apache JMeter as a load generator. And in our scenario, we are going to load our servers with 500 threads, and each one with 200 iteration and 5-second ramp-up time. And our nodes or auto-scaling group, which was consisting of three virtual nodes, is on T2.small EC2 instances, which that means each of those has 2 virtual CPU, and for each pod, and I'm gonna just give a simple explanation, just to which each pod is an instance of the Platform Dash application. So for each instance of our pods, we assign 200 megahertz CPU, and we are simply sending a simple GET request. And as you can see here, this is our horizontal pod auto-scaling configuration we defined here. If the CPU utilization on each pod reached the 40%, this is the threshold, just consider a minimum number of pods and the maximum number of pods and play just between this range. Yeah, exactly. If you reach 40%, just scale it up, scale it up until what number? Until 10 pods. So here is the result that actually we did all this burden and yeah, exactly. We did all this burden to making an auto-scaling infrastructure, but the result that we got is so fascinating. The scenario 1 was just a single pod. Scenario 2 is an auto-scaling infrastructure consisting of 1 to 10 pods. But as you can see here, the 99 percentile of the response time here for the scenario 1, which was a single pod, is 4 seconds, but in scenario 2 is 15 seconds. So from the response time aspect, actually the scenario 1 is a winner. But exactly, wait a minute, it's not all the story. And even as you can see here from the percentile graph that we have here, in the scenario 1, as you can see here, exactly, from 96, maybe 95, the response time is increasing. But in scenario in scenario 2, is from maybe a little before that 95, maybe 91, 92. But if we go take a look deeper on, for example, the response time graph, as we can see here, in the scenario 1, we have a response time here. Actually, unfortunately, I cannot show you. Maybe I should have just pointed out here a number of response time. That would be better. But if you can see here, the response time is increasing when we reach the maximum number of active threads here. And that's when our pods or our server stop working, because there's a huge backlog of the requests. And but as we can see here on the scenario 2, we have this kind of, I don't know, maybe piercing, maybe jagging patterns. So spikes, yeah, a spikes pattern. So the thing that we learned from this scenario is that because this gap that you can see here is when our system start to adding a new pod. And in this case, we reach from 1 pod to 4 pod, and the system make it from 4 pod to 8, and eventually from 8 to 10 pod. So during adding each pod, so we can see a huge number of backlog of the requests. So that's when we get high response time. But after adding a new pod, the response time is way much better than the single pod. So I really do like to put these two graphs, next to each other, which is this column exactly is for scenario 1, this is for scenario 2, and this is the number of transaction actually were during the time. And this is the number of transaction, and this compared to the thread. And we can see here, for example, in scenario 1, we have failure transaction because the service stopped working when we overwhelm the service. But in scenario 2, we don't have any failure transaction. And even in scenario 1, we barely, reached the 1200 transaction per second, but in scenario 2, we reached 3200 transaction per second. So overall, if I wanted to make a conclusion here, during adding a new pod, we find out that it's going to be the scenario 1 will perform better. But after adding or scaling off the scenario 2, which is the auto-scaling infrastructure with multiple pods, is going to be, is going to perform very much better. And that's it. That was a finding from the auto-scaling infrastructure.
Okay.
Yeah, I'm going to pass it to
that was a
Imran.
long presentation. So I'm just going to wrap it up real quick. I'm going to talk about the challenges and the future works of our project. So for the challenges, first of all, as first mentioned, we had problem with our Amazon Academy account. We couldn't really use EKS because we needed AMI role for Amazon EKS and also for ElasticMapReduce. So yeah, Ali was brave enough to use his personal account for his testing. So yeah, and also the EMR service and the S3 data access, it's very costly. As you can see, $10 per day. If we kept it running, we didn't. Also, to do the Java, to do the data processing in Java, that was also pretty hard. And also the Kubernetes. I was familiar with Docker. We were familiar with Docker before, but yeah, we didn't really use EKS specifically for Kubernetes, so that was challenging for us. And for the areas of future work, so we don't really have a nice user interface for all the tests that Forrest did and explained. So having a nice UI would be a nice addition to the project. Also, the ElasticMapReduce could be implemented with a Python framework called PySpark. That is a Apache Spark framework in Python. Also, for the ETL test, we could have more data sets. We had a limited data set from just one company. If we had more data set from different company, that would be better for the models. And we have made the Docker. We could use some CI/CD tools. So right now, we haven't really used any CI/CD tools except the Docker Hub. We have made the Docker image ourselves and then pushed it to the Docker Hub manually, but that could be automated using some CI/CD tools like Jenkins, GitHub Actions, or Travis CI, some other cloud CI/CD tool. And yeah, that is about it. Thank you.